All right, so this video I'm gonna explain Bernoulli equation with like everything that you could possibly do with it, including like pump head, turbine head, and like the losses. I'll go over like pump curves, give a couple examples I go along. Yeah, if you learn anything from fluids, learn Bernoulli. It's like applicable to literally every fluids application that you're going to deal with in industry. Yeah, okay, so let's start out by writing the equation. Oh. Let's not do this part yet. Cool, that is literally it. This is the simple version of the Bernoulli equation. So all this is conservation of mass. So like if, I'm not supposed to show that yet. In like physics, you learn that if you have like a box with mass m and it's got, okay, and you drop it a set distance, you can calculate the velocity. If you drop it, it'll be, what is it? 1/2 mv squared equals mgh. And that's like conservation of energy. All of the height energy goes into velocity. So Bernoulli is literally this exact same concept, but for fluids. So let's go over a couple examples. Okay, so let's say, what should we say? Let's say you have a tank on a hill and you have a pipe that pipes the fluid down and shoots it out. All right. Let's say the fluid level is right there and you have a height. What should I call it? I won't call it anything, but you get the idea. So what's the velocity gonna be? What's the velocity that it shoots out gonna be? So we could use a Bernoulli for that. The way we would use it is we would say inside of the tank, we're gonna assume that it doesn't have relative pressure. It's got absolute pressure, but let's assume it doesn't have relative pressure. So P equals 0. It doesn't have velocity because it's just sitting there. It does have a Z. Let's call it height. And then when it shoots out here, it also doesn't have a P, or pressure, because right along this edge, it's at atmospheric pressure. And like, even when it's shooting out here, it's at atmospheric pressure, same as up here. So pressure equals 0. Velocity now equals some velocity. I'll call it V2, which is what it's called up there. And it doesn't have relative height. Z2 equals 0. And P1 and V1. 2, 2. Okay, so we could simplify this equation. P1 equals 0, that term goes away. V1 equals 0, that term goes away. This Z1 is H, but I'll leave it there for now. P2 is 0. V2 exists, but Z2 is 0. So we end up with, I'll call it H. H equals V2 squared over 2G. Oh. And, oh dang, my arrows suck. And this can be rewritten as V2 square root of 2gh. Which actually, now that I think about it, with the example before with the box of mass m, 1/2 mv squared equals mgh. And if you solve for it, you get v equals 2gh squared. So it's the same number, which should hopefully make you more confident in using this equation. So that's the first example. Is there another good example I could do? Well, okay. I mean, frankly, if you can do this example, you can do any example. The hardest part is picking points, because if you pick a point, if you pick your point 1 right there and your point 2, I don't know. You keep your point 2 there, let's say. So you keep it there. You're going to struggle because you're going to have a pressure here, because this pressure is going to be, what would it be? Might be that. I mean, we could literally use this equation to figure out this point and that point. Let's just do that, I guess, since I already dug myself in this hole. All right. So let's call this H. I know this one's also H, but I'm going to erase that one. So let's use a Bernoulli for this. So we're going to have same state 1. I'm going to call this one state 2. So what do we have at state 2? We would have a velocity. So V2 equals V2. P2 equals P2. We would have a pressure because there's a depth. Z2 equals, let's assume it's relative, so it'd be 0. So, I mean, same idea as before. That goes away, that goes away, and that goes away. And then we're left with H equals P2 over density gravity plus, oh man, V2 squared over 2g. So now the energy, the height energy, is split between pressure and velocity. And there's not a super straightforward way of how to get this easily just with this equation. So I'm going to just leave it here. But that is effectively how you use the simple Bernoulli equation. Okay, now let's make it a bit more complicated. I want you right there. Pump. I'm gonna move all of it over to the left. All right, so I added 3 terms. I added a pump head, turbine, and a loss. So let's start with the loss. Okay, so the equation for H loss is the sum of, that's a bad sum. That's even a worse sum. All right, sum of V squared over 2G KL plus sum of v squared over 2g f L over d. So what is this saying? It's saying a couple of things. So actually, let me redraw the example I just erased. I'm gonna not redraw it the exact same actually, but you get the idea. So this first half is called minor losses, and the second half is called major losses. So what are minor losses? So those are things like a bend in a pipe, or if you're going through like a flow orifice, there would be a loss term associated with that as well. And these constant, like it's literally just a number. You can Google tables of loss. So maybe for a 90-degree bend, it would be like, I don't know, maybe like KL equals 0.7 or something. I don't know. It's on a table somewhere, you can find it. But yeah, so this is basically saying the minor term is proportional to the velocity of the fluid going through and gravity and that loss coefficient that you look up in a book. Okay. So, just as a quick example, let's say you have a straight pipe, and then let's say you have a pipe that turns 2 times. Which one's gonna have a higher minor loss? Well, it turns out the second one, because you have a bend there and you have a bend here. And each of those has a loss coefficient, so then you would do v squared over 2g. You'll probably group them in this case. L1 plus k L2. And maybe they're the same because they're both 90-degree terms, so then it'll just be like 2kl. But yeah. So that is the minor losses stuff. So what about major losses? It's also a pretty simple-ish concept. So you have a pipe, there's friction. This like if we zoom into the bottom part of the pipe, there's a bit of friction there. And that will take energy from the fluid flow. So that is what this part, the major losses, represent. So what is it a function of? It's a function of the velocity. So higher velocity going through the pipe means higher major losses. And it's a function of L, so the length, which makes sense because if the pipe is longer, it's going to lose more energy. And the diameter, but it's 1 over the diameter, which also makes sense because if the diameter is like huge versus small, more of the fluid will be hitting the wall in this top picture than the bottom picture. So it makes sense that the major loss would increase when the diameter is smaller. And then it's also a function of this F coefficient. And this is basically, I mean, if I redraw the pipe with the little squiggles, it's basically how big are the squiggles or how little are the squiggles. And the way this number is found, it's basically given to you. Like it's measured in a lab. So you kind of use this table and it looks like there's a lot going on. But it's kind of simple to understand. So we're looking for this term on the left. The way we get that is first by calculating this number, the over d. So E over d, and d is the diameter. It's the same diameter that you use here. And the E number, they'll give you, like in a problem statement or whatever, they'll give it to you. Or they'll ask you to solve for it and give you everything else that you need. Yeah. So you can calculate this number. Let's say we find out that ours is 0.001. So we could just draw the line straight over and say our friction factor is 0.02. And that could be correct if our Reynolds number, which I don't know if you remember the Reynolds number or not, it's density, velocity, diameter over the mu number. If you're at a high Reynolds number, you can kind of just assume that it's straight across. But if you're at a lower Reynolds number, you can't really assume that. You gotta follow the curve upwards, find your Reynolds number, and then draw a line over. The funny part is you don't know your Reynolds number until you completely solve the problem, because you get the F coefficient, then you solve the problem. Typically you solve it for V2, because that's typically, like in this problem, that's what we were solving for. So we had to find that. And then you go back and check. Then you plug in that V2, and let's say you have a high V2. So the V2 landed you somewhere with a Reynolds number around there, like around here. Then you're fine, because then you can just assume you went straight across. But if your V2 was like over here, then you'd have to re-solve the problem with the new friction factor. So you kind of have to go back and resolve it, which kind of sucks, but that's the only way to do it. Okay. So that's how you get every term in the major loss. So I guess as a quick example, let's say you have a pipe and then it expands. And it expands again. So you're going to have a v squared over 2g f L over d. So what's going to be the same here? Well, let's say this is L1, L2, L3. So L you can just plug in. F will change and D will change because F is a function of D. So that number will change because the diameter is changing. D1, D2, D3. And the velocity will change also, because if you're assuming conservation of mass, you're going to have, what would you have? VA equals VA. And you're going to have a bigger area as you go more to the right, which means your velocity is going to be lower. So like most of the terms in this equation are going to change as you move through the pipe. So you're gonna, that's why it's the sum of them, because you have to sum all of them. So, all right, that's all of loss stuff explained pretty much. Now, for the pump term and the turbine term. So, typically, the way this will work is you'd be given this drawing, you'd be given the pipe diameter, you'd be given the E value to get the major loss, and you'd be given the KL for that bend. And then they'd ask you, this is a bad problem the way I drew it out. Let's say you have a pump and it pumps fluid up a hill, and you want it to shoot out with some set V2. And there's a V1 over here also. And then there's a Z2, like a height. I'm not calling it H because H is like the loss and the pump head and all that stuff. So let's work through this problem. So what do we have? Let's assume well, okay, they'll also give you a pressure, because when you pump fluid through a pump, it pressurizes it, kind of. But anyways, you'd solve for it. You'd be given the diameter, you'd be given that, you'd be given the loss coefficients, and then they'd say, what size pump do you need to do this? And that's like a real world question. How do you spec that? So using the Bernoulli, you'd solve for the H pump and you get a number. Like, let's say it's, I don't know, what's a good number? Let's say it's 60 feet. I hate that they use feet, but they do. But you get let's say you get 60 feet, and you get that the V2 is some number that when you combine it with the diameter to get the volumetric flow, volumetric flow is Q, you get, what's a good number? Let's say 500. 500 gallons per minute. So let's say you solve it and you get your V2 and you get your H pump and you get your, well, you know your diameter, and you get that the pump head required is 60 feet and you need to pump 500 gallons per minute because that's what the customer is demanding. So you come over to your pump curve. This is a pump curve. P 60 feet equals 500. Okay, so where does that land us? That would land us right here, right there. Cool. So what size pump should you do? Should you do an impeller of 7 inches or of 7.5 inches or 8 inches or 8.5 inches or 9 inches or 9.5 inches? Well, you should do to be safe, you should do 9 inches in this example. But I guess, all right, what is this pump curve showing? So these are diameters of the impeller. So basically, how big is the pump? These lines are efficiency lines. So ideally, you want to be at the highest efficiency. So where is that? That is somewhere in here. Probably right there. So you want to set up your conditions such that you can end up right here. So you'd want to design the system, or, well, okay, you could either design the system around that, or you could find a pump where its best efficiency point is right there. Because in our example, we were at like halfway between 78 and 79. So like 78.5% which is really close to the 79% best efficiency. But so probably for this it would be fine, but ideally you want to be as close to this BEP, best efficiency point, as possible. Okay. I guess one other thing with the pump curve. So there's this term, NPSHR, and that stands for net required, net positive section head required. So at our point, we require maybe, I don't know, let's say for us it's 8 feet. So that means that this, whatever pressure we have, and whatever V1 we have, and whatever Z1 we have, has to add up to 8 feet worth of head. And the way we would do that is we would do P1 over NPSHA. And this is net positive suction head available. And we want the available number to be greater than 8 feet. If it's not, we're gonna cavitate, and that's a whole other issue. But basically, that would break the pump. So you don't want cavitation. That means the pump is pulling a vacuum and well, what actually happens? It'll vaporize the water, and it'll turn it into, well, a vapor, and that'll expand it, and that'll cause bubbles to form, and that'll freaking blow up the pump from the inside. It's pretty exciting when it happens, but it's a big failure. Yeah. That's kind of all you need for this. Cool beans.